So we want to keep exploring our free scalar field a bit more. And the thing that we're going to start with is, again, exploring causality. Now, remember previously we tried to build a single particle description, and we found in that description that particles could travel faster than light. And that meant we could send information faster than light could travel. And as we've discussed, this is unacceptable because it means we're able to violate causality. Okay, so a natural question to ask now is, can particles move faster than light in our new theory? Okay, so that's what we want to explore now. How fast can the particles move that are described by our free scalar field? So we're going to start off, as always, with an expression for our free scalar field, the mode expansion. So this is given by an integral, v3k over 2 pi cubed to omega k. So that's the Lorentz invariant integration measure. Then we have our Lorentz invariant oscillator, alpha k. It is multiplied by e to the minus I k dot x plus alpha k dagger e to the I k dot x. This really is the central formula. So it would be very good if you're getting familiar with this to the point where you can write it down without looking at the notes. In this formula, omega k is equal to k dot k plus m squared square rooted. So that's what omega k is. And let's just write out, what do we mean by k dot x? Well, k dot x is omega kt minus spatial k dot spatial x. When we want to think about what can our field do, well, there is a creation and an annihilation operator. What this particle does, this is a local theory, so it does something at position x. And what can it do? It can create or destroy a particle at event x mu. So that's what our field can do. Good. Okay, so let's see. We start off simply with the vacuum, naught. And this is the state with no particles. State with no particles. Then the first thing that we can do is we can act with phi of x on the vacuum. Now, remember that alpha k acting on the vacuum just gives us 0, whereas alpha k dagger on the vacuum is a one particle state. So when we act with phi of x on the vacuum, the term with the alpha k will just annihilate the vacuum, but the term with the alpha k dagger will create a particle. So this is a state with one particle, and it is created at x mu. Good. Okay, now we could study what happens if we take the field phi of y and we apply it to the state. So again, there are two things that can happen. So first of all, because phi of x acting on naught is a one particle state, when phi of y acts on this state, it could produce a naught particle state if it annihilates the particle. So this is what we get by the action of alpha. Let me maybe color code things a little bit. By the action of alpha, okay? And what I want you to remember is that phi of y, it contains alpha and alpha dagger. So the action of the alpha could produce a no particle state when it acts on phi of x naught. And apart from the no particle state, we could also have a two particle state. And that is by the action of alpha dagger. So the alpha dagger inside phi of y might produce another particle so that we get a two particle state. And let's just even be a little bit more explicit. This naught particle state, how was it obtained? Well, we created a particle at x mu and destroyed a particle at y mu. How was this two particle state created? Well, we created a particle at x mu, and then we created a particle at y mu. Okay, good. So we've got this naught particle piece and this two particle piece sitting inside this state. Now, consider the following. So here's a space-time diagram. So this is t. This is x. Imagine we've got some event here. This event is x mu. And let's draw the light cone of x mu. So there's the one arm of the light cone. There's the other arm of the light cone. Now, we could ask ourselves, what is the amplitude to detect a particle at this position y mu? Okay, because the particle is outside of the light cone, if the particle that was created at x mu is detected at y mu, so if this amplitude is not equal to 0, then it means particles can move faster than light. And this is exactly the question we wanted to ask. So we see this naught particle piece of the state, where we've created a particle at x mu, destroyed a particle at y mu. This is exactly what we need to answer our question, can the particle move faster than light? So we want to isolate this naught particle piece. Well, the way to do that is if we compute the overlap with the bra 0, well, we know that the no particle state and the two particle state is orthogonal, so this will vanish. Whereas this term is no particle against no particle, this is non-zero, so that in fact, by dotting our state, by taking the overlap of our state with bra 0, we get exactly the quantity that we are interested in. So just to summarize, naught, phi of y, phi of x, naught, this is the amplitude that a particle created at x mu is detected at y mu. We'll continue in a moment.